Should I start?
Yeah.
Okay, so hello in the second part of this talk. So in the first talk, we have defined quasi-function manifolds. We have seen how different interactions between these quasi-function manifolds and the data on their boundaries. Now we have seen many statements about that. Now we will see other statements in the same spirit of what we have seen in the first talk. So now we will start by this theorem stating that if I take a measured lamination with some conditions on the weights that must not be more than pi, because it makes sense, because in a pleated surface you cannot bend it. You can't have you can't have bending more than pi. And if we take any Riemannian metric which with curvature strictly bigger than -1, then we can find convex hyperbolic metric on sigma times 0, 1 that induce the metric the metric h on sigma times 0, 1, and it makes the lower boundary sigma times 1 a pleated surface which has structure which has bending lamination equal to mu. Of course, again, everything is inside some quasi-function manifold. Yeah, so this is the picture that we will have. The metric is realized as the induced metric in the upper boundary, and the lamination is realized as bending lamination in the lower boundary. So, of course, one of the components will be the boundary of the convex core of this quasi-function manifold. Similar statement is on the third fundamental forms. So if we take mu to be a measured lamination with the condition that no closed leaf has weight bigger than pi, and we take H star to be a Riemannian metric on sigma that satisfies the condition of the realization of third fundamental form, which are the curvature must be smaller than 1, and the length of every closed geodesic contractible geodesic is strictly bigger than 2 pi. Then we can find the convex hyperbolic metric on sigma times 0, 1 that induce H star as third fundamental form in the upper boundary, and induce the lamination mu as bending lamination on the lower boundary, mu plus. So in both statements, we don't know uniqueness. We just know existence. We still don't know nothing about the uniqueness. Another theorem, the statement that can be seen as a limiting case of this of the first one, we will see why limiting case, is that if I take a measured lamination and if I take a hyperbolic metric on sigma, then I can find the quasi-function manifold that induce H as the induced metric on the upper boundary and induce mu as the bending lamination in the lower boundary. The same thing is also true with the conformal structure. So if I take mu to be lamination and measure lamination and C to be a conformal structure, I can find a quasi-function manifold that the bending lamination on the upper ideal boundary is C is the conformal structure on the upper ideal boundary is C, and the bending lamination on the lower boundary, which will be the lower boundary for the convex core, is the measured lamination mu. So here also for these statements, we don't know uniqueness in the general case, but we can say something. We can say that if I take mu to be measured lamination, and if I take H to be hyperbolic metric, then I can find some delta that depends continuously actually on mu and H, such that if I take any small scalar t, then there exists a unique quasi-functional manifold that realize H as the induced metric on the upper boundary of the convex core, and induced mu as the lower, as the induced lamination on the lower boundary of the convex core. Yeah, we will talk about, we will sketch the proof. We will talk about the sketch of the proof of all these statements. Before that, we will define the notion of K-surfaces. So what we mean here by K-surfaces, by K-surface, so we mean by K-surface here, we mean a surface sigma which is embedded into for us it's always quasi, we will take quasi-functional manifold. So it is surface sigma which is embedded into M, the quasi-functional manifold, which has constant Gaussian curvature equal to K. So if it has a constant Gaussian curvature equal to K, we say that it is a K-surface. And what theorem by Labourie has shown that if I take quasi-functional manifold, then the complement of the convex core is foliated by K-surfaces, where K vary between -1 and 0. So if I take quasi-functional manifold, I take each complement, the complement of the convex core will be 2 components, and each component is completely foliated by these K-surfaces. And K vary between -1 and 0. So this surfaces that has curvatures K to foliate the complement of the convex core. So as you can see here in this figure, but when K vary between -1 and 0, then this surface will also vary from the convex from the boundary of the convex core until the ideal boundary, and it is a foliation. They're disjoint and cover everything. Yes, and also we know we know what happens to the matrix on the K surfaces when K varies. So when K vary to when we ask K to go to -1, then these surfaces with their induced matrix converge to the boundary of the convex core with the induced hyperbolic metric. And when we ask K to go to 0, then this K surfaces with the conformal structure induced of their induced metric converge to the ideal boundary with its conformal structure. So in other words, these K surfaces, they are like a path that relate between the conformal structure on the ideal boundary and the induced metric on the boundary of the convex core. You ask K to go to 0, you go to the ideal boundary with the conformal structure, and when you ask K to go to -1, you go to the boundary of the convex core with this induced hyperbolic metric. Similar thing is also true for third fundamental forms. So if you ask K to go to -1, so maybe it's better to start with 0. If we ask K to go to 0, then the third fundamental, then the K surface with the induced third fundamental form on it will go to the ideal boundary with its conformal structure. And when you ask K to go to -1, the K surface with the third fundamental form will converge to the boundary of the convex core with the measured lamination. So now, of course, the question is like, how can a metric converge to a lamination, to measured lamination? And the answer is like by something called length spectrum. So you take if I take closed geodesic in sigma, then the length of this closed geodesic by the third fundamental form will converge to the weight induced by the measured lamination on sigma. Yes, so as we have seen in the first part, measured lamination induce weight on each transverse arc. Yes, so the convergence here is in that sense. So again, these third fundamental forms, this K-surface induced with third fundamental forms are like a part that relate the conformal structure on the ideal boundary and the boundary of the convex core with induced matrix. Whatever with the bending lamination, sorry. Yeah, so now we can start our sketch of the proof. We still have to give another statement. This is a theorem by Chen and Schlenker. So in here they have shown that that if you take H and H star to be matrix, H satisfies the condition of first fundamental form, that is the curvature is bigger than -1, and H star satisfies the condition of third fundamental form, that is it has curvature smaller than 1 and strictly smaller than 1, and each contractible cross geodesic has length bigger than 2 pi. Then the authors, the Chen and Schlenker, have shown that you can find a unique convex hyperbolic metric on sigma times 0, 1, such that the induced metric on the upper boundary is H, and the third fundamental form on the lower boundary is H star. So it's like people already did statements about first fundamental forms, third fundamental forms, and here they take like different data and see if they correspond to the same quasi-function manifold. Yeah, so the main the K lemma that we will focus on, we will use to get the statements that we have announced in the beginning of this talk, is the following properness statement. It says that, so here, this lemma basically says that the map that associates to a quasi-function manifold the induced metric on the upper boundary of the convex core and the bending lamination on the lower boundary of the convex core is proper. So in other sense, if I take a sequence of quasi-function manifolds and I assume that in this sequence the induced metric on the upper boundary converge to some H, and also I assume that the bending lamination on the lower boundary converge to some lamination L. With the necessary condition on the lamination, of course, we can't have some weight bigger than some diff with weight bigger than pi. Then up to extract a subsequence, we will have that our sequence of quasi-function manifold Qn converge to some quasi-function manifold Q that has H and L as the induced data on the boundary of the convex core. And to do this, we will need a theorem by Sullivan. So Sullivan says that there is a universal constant K, which is close to 2, but it is not equal to 2. It was conjectured that it is exactly 2, but eventually Markovich, I think, has shown that it is not equal. He gave a counterexample and shown that it's not 2. So anyway, the theorem of Sullivan says that there is a universal constant that doesn't depend on the quasi-function manifold, such that the Teichmüller distance between the conformal structure on the ideal boundary, and the induced metric on the boundary of the convex core is less than k. So if you take a look at both of the conformal structure and the induced metric are points in Tashmiller space, and the Tashmiller distance between them is smaller than a certain universal constant that doesn't depend on quasi-functional manifold, and actually it also doesn't depend on the surface sigma. Also, if I take another surface sigma, it will still the same. Yeah, so here we can deduce that if we show that if the matrix on the boundary of the convex core are in a compact subset, then also the conformal structure on the ideal boundary will be on a compact subset of Tashmiller space because they have bounded distance. And it's exactly what we will use here. Just a moment to show. So in the lemma by hypothesis, the metrics on the upper boundary converge to something, so they are fine. And the bending eliminations on the lower boundary converge to some elimination that doesn't have weight that has doesn't have a weight leaf of weight bigger than pi. And so exactly, so here what will happen? It will happen that if the matrix on the lower, the induced matrix on the lower boundary diverge, then the eliminations on that boundary won't converge to a nice elimination. We will have something like that. We will have some big bending. Or precisely, we will have some leaf with weight bigger than pi, which is not allowed by the hypothesis of the theorem, by the hypothesis of the lemma. So what we will get that under the hypothesis of lemma, then both metrics on of this sequence Qn on the boundary of the convex core, the induced metric on the boundary of the convex core, they must be in a compact subset. And by Sullivan theorem, also the conformal structures on the ideal boundary must be in a compact subset. And this is enough to deduce that it is enough because of Bers' theorem that identified quasi-functional manifolds and the quasi-functional manifolds and their ideal boundary. It's enough to deduce that the quasi-functional manifolds converge up to some subsequence because the conformal structures on the ideal boundary converge. Yeah, then using that we will see how we will prove the different statements. So for example, if we want to realize one metric and one bending elimination, what we will do is we will use Chan and Schlenker theorem. And it says that when I take H and H star with the necessary conditions, then I can realize one as a first fundamental form and H star as a third fundamental form. So we will take H, the metric that we want to be in the upper boundary, and we will take H and star, a sequence of metrics that converge to the measured elimination mu and satisfies the condition of third fundamental form. And we use their theorem to realize the matrix H as first fundamental forms and H and star as third fundamental forms. And then we ask when n get bigger, we will get that the metric on the boundary of the convex core here is we will still find because we have that the projection of this red surface into the boundary of the convex core is 1 Lipschitz. So this guarantees that the metrics on the boundary of the convex core won't diverge. And also we have similar thing with the third fundamental form and the measured elimination. So the projection is also 1 Lipschitz. So this guaranteed that the measured elimination on the other boundary of the convex core won't diverge. And this is in order to use the lemma to deduce that our sequence of quasi-function manifold will converge up to extract something. And this limit will realize H as the induced metric on the upper boundary and realize mu as the bending elimination on the lower boundary. Yeah, now if we want a similar statement with third fundamental form, so we will need this lemma saying that so if I take sigma inside the quasi-function manifold, then the third fundamental form and the first fundamental form are dB Lipschitz, and this d depends only on the curvature of this surface. So so it depends on sigma on the third fundamental form and the first fundamental form only. And so this is in order so if you want to realize third fundamental form and measure elimination, we will use Labourie theorem. So in Labourie theorem, and we will take H star, the metric that we want to realize as third fundamental form, and we will take also Hn star, a sequence of metrics that converge to mu. We will realize both of them as third fundamental forms. And since H star is dB Lipschitz with the first fundamental form, then the first fundamental form here won't diverge, and also the induced metric on the boundary of the convex core won't diverge. And it's similar with H star and mu. So here we guaranteed that the sequence of bending eliminations on the boundary of the convex, the lower boundary of the convex core won't diverge, and we can again can extract a subsequence of quasi-function manifolds that converge to some quasi-function manifold which realize H star as third fundamental form in the upper boundary and realize mu as bending elimination in the lower boundary. And so now how to deduce theorem about when H is a hyperbolic metric or when C is a conformal structure. So if we take a hyperbolic metric and the measure elimination that we want to realize, it's sufficient to take a sequence of metrics Hn and make them converge to H. And when we make this matrix Hn converge to H, then the quasi-function manifolds will converge to something that has H as the induced metric on the boundary of the convex core and mu as the bending elimination. And this is the same is true with C. So we need to take for example, matrix with curvature Kn that Kn converge to 0 and Kn converge to 0. And mu is measured elimination in the lower boundary of the convex core, and when we take n2 goes to infinity, and yeah, we need also to assume that the conformal structure of this Hn converge to C. We will get eventually quasi-function manifold that has data as the ideal boundary at infinity is C, and the bending elimination on the other side of the boundary of the convex core is equal to mu. Yeah, so this was for surjectivity statements. Then we will talk, we will give a sketch about the proof of the partial proof of uniqueness. So yeah, so measured eliminations form a set on the measured eliminations on some surface sigma forms a set, but this set doesn't have any natural differential structure. But still, that this set of measured elimination can have some structure which is called piecewise linear, and we still can do analysis on the set of measured elimination because the structure of piecewise linear, this piecewise linear structure allows us to talk about tangent vectors. So we can still do analysis, even if it is not as nice as differential structure, but it is useful also. So here we are stating a theorem by Bonaho, So Bonahon says that if you take quasi-function, the correspondence that associated to quasi-function manifold, the hyperbolic metric and the measured elimination on the same side here. So yeah, this is not to be confused with the other statement when we take h on one side and mu on one side. Here we take h plus and mu plus in the same side. So Bonahon has shown that this correspondence is a bitangentiable homeomorphism to its image. Yes, so bitangentiable, it's like differentiable, but since we don't have a differential structure on the space of measured elimination, we have to ask less. And also, again, Bonahon also showed that if I take the space of all quasi-function manifolds that have measured elimination mu on the measured elimination equal to T mu with T T bigger or equal to 0. Yeah, so we allow T to vary. So here it can be like mu, 2 mu, 3 mu, anything which is realizable. Bonahon has shown that the set of quasi-function manifolds that has T mu as bending elimination on the upper side, they form a submanifold inside the set of quasi-function manifold. It forms a submanifold with boundary, and it has dimension 6G minus 5, which is Teichmüller plus 1. So here we are fixing elimination, so it makes sense because we will have the other boundary which vary, and we are multiplying by t, so we will decrease along also one dimension. Well, we will add one dimension, sorry. So it makes sense to have it to have the dimension is Teichmüller plus 1, and also the boundary of this b plus, the b plus mu, is the Fuchsian locus, which also makes sense because when t goes equal to 0, we don't have bending, and when we don't have bending, we are in the Fuchsian case that we have seen in the first part. We will have just one totally geodesic surface. Another theorem by Dumas and Wolf, Bonahon. So Bonahon have shown something, and Dumas and Wolf deduced that, continue the argument that if I take the set of quasi-function manifolds that have H as the metric on the lower boundary, I take all the set of quasi-function manifolds that have H as the metric on the lower boundary. Then this set, this subset is a C1 submanifold of dimension 6G minus 6, which is dimension of Teichmüller space. Yeah, so here we know that it is C1 submanifold, but it also interesting. Yeah, as far as I know, it's still open. We don't know if it is in the general case. We don't know if it is. It can be more than C1, even if yeah, it was shown that it is not more than C1 when sigma is the punctual torus. Yeah, I think. But in general case, it's not shown, even if it seems that there is no hope that it is more than C1. Yeah. Yeah, so here we will use some technical lemma to deduce this local this partial uniqueness statement. Is that if I take a curve, a C1 curve in B plus muse, that is that the bending elimination on the upper component to the convex core is of the form T mu. I take such a curve. And when I see it's well, the infinitesimal data of this curve at 0, yeah, but here I see on the other boundary, we will get we will have h dot times mu prime, and this mu prime, it depends only on mu. also in the other side, we have that if I take curve of manifolds that has constant induced metric h, then of course infinitesimally it will be the data will be 0L, because the first coordinate that corresponds to metric is fixed, and the other coordinate it can be just anything, a measured elimination. I forgot to say that the tangent space with the measured elimination at the elimination 0 is the measured elimination itself. And so when we combine these two facts, 1 and 2, we get that this is the important the main key that one should know, is that the manifold the manifold of quasi-functional manifolds that have bending elimination of the form T mu on the upper boundary of the convex core, and the set of quasi-functional manifolds that have induced metric H on the lower boundary of the convex core, they intersect transversely at the functional locus. And from that, we will deduce that there is a neighborhood of the functional locus, and in where the intersection of B plus and minus is a submanifold of boundary of dimension 1. This allows us to deduce that for any metric H and any bending elimination mu, we will get some curve of quasi-functional manifold that has boundary data on so if you take QT, then you will have metric H on the lower boundary and bending elimination T mu on the upper boundary. And so when we take all these curves, the union of all of these curves, it will form a neighborhood of the function locus, in which when we know the metric on one side of the convex core and the measured elimination on the other side of the convex core, it's we know in which curve we are, and then we know about what quasi-functional manifold we are talking about. Yes, so as far as now, we can deduce that there is a neighborhood of the function locus in which the map that associate an induced metric and the measured elimination is injected. But we don't know if there is another neighborhood. We don't know if this map is not injective inside this neighborhood. But what we can see, we can see that we can see that if the bending elimination is small enough, then it's sure that we are in this neighborhood, because when the bending converges to 0, then the quasi-function manifold converges to something function. And so from all of this, we can we deduce that we deduce this partial uniqueness theorem is that when we take a measured elimination with and hyperbolic metric, then we can ask we can ask if we ask the elimination to be small enough, it's quite to multiply the elimination by some t smaller than this delta mu h. Then there exists a unique quasi-functional manifold that realize H as the induced metric on one side, and realize T mu as the bending elimination on the other side. So that's all what I wanted to say. Thank you for listening.
Thank you, Abderrahim, for this very nice presentation. So, are there any questions or remarks, comments?